I'm going to make a pretty bold move here by bringing up a topic that most people didn't like from intermediate algebra, and that topic is conics. I want to talk about graphing conics. And before you stop the video and decide you're not going to watch this one, I'm going to try and keep it fairly simple. I'm going to try and make some connections here. So let's see if I can be successful here. So the first thing I want to do is I want to put up the general form of several conics that you learned before. Alright, so here they are. I don't think you need to write these down. I'm hoping I can simplify them a little bit later. I want to remind you about these graphs. First, with a circle, to be honest, I hope I don't need to review this. The idea was whatever number was over here, that was the radius of the circle, right? So if we had 25 over here, you have a circle that's centered at 0 with a radius of 5, right? The ellipse is where things got a little bit more interesting, right? In an ellipse, these numbers on the bottom, A and B, I actually kind of gave creative names to. I called A the x radius. Totally not a precise mathematical term, but it works well enough. So A was the x radius, and B was what I called the y radius. Right? So as an example, if you had been asked to graph x squared over 9 plus y squared over 25 equals 1, that meant that you sort of went to your graph, you went 3 in the x direction, in both x directions, and sort of put points there. Right? Then we went 5 in the y direction. So you got a point there and a point there. And you sort of connected all these dots and got this ellipse shape, right? And the idea was that effectively an ellipse is just a circle that has two different radii, one that's an x radius and one that's a y radius. You know, we could have taken the circle and we could have put divided by r squared on both of these and set it equal to 1 if we really wanted to. And doing that would let us see that the circle and the ellipse are really kind of the same thing. The hyperbola is where things got a little bit more complicated, and I hope to show you here that it shouldn't have been. So let's move down and take a look at one of those. So the difference on a hyperbola, the difference between ellipse and hyperbola, is that the ellipse had a plus in between, the hyperbola had a minus in between. And the idea was that if there was a minus, if the x came first, then it was a horizontal type hyperbola, and if the y came first, then it was one of these vertical type hyperbolas, right? And the way that we graph these things, I'll just go down and do one really quick example for you. The way we did these things is if someone asked you to graph y squared over 25 minus x squared over 9 equals 1, we would sort of do the same thing we did for the ellipse. We would start by graphing the x radius. We'd graph, you know, to the left 3 and to the right 3. You'd sort of, you know, put a little marker there. And then you'd go up 5 and down 5. And then we had this business of sort of making this dotted box, and then making the asymptotes that went through the corners of the thing. Hopefully this is bringing back memories. And then you would sort of draw the hyperbola into the space that we had here. And because the y came first, we're drawing this on the top and the bottom. And so you sort of had a hyperbola that looked like this. And the thing that made this lesson so weird in intermediate algebra is we had never dealt with things that had like two branches to them and all kinds of crazy stuff like this. So I'm actually not going to be going directly into this. I want to connect to how these things can be functions. And the way that we make these things functions is effectively by solving them for y. So I'm going to be looking at that in the next slide. So there's a lot of information here. You probably want to write these things down. When you have a circle that's x squared plus y squared equals r squared, if you solve for y, you get this thing. So what does that mean to us? That means when you see a problem that says, hey, what does y equals the square root of 9 minus x squared look like? The answer is, it looks like a circle. It looks like the function version of a circle. And in fact, it's interesting, this square root should have a plus or minus on it. Right? When you take a circle, you'll either get the top half of the circle, or you'll get the bottom half of the circle, depending on whether the square root has a plus or a minus on the front of it. So what I'm getting at here, and this is the thing that you sort of either need to memorize or sort of grapple with, if you are ever asked to graph a function that has the square root of a constant minus x squared, that came from a circle, and so you can graph it as such. Right? I can say very similar things about hyperbolas. You'll notice that this equation up here that I'm giving you for a hyperbola is rather different from the one that I gave you earlier. And really all I'm pointing out is, and if I use the one I gave you earlier, it gets a lot more complicated. All I'm saying is that we can look at a special type of hyperbola that has x squared over r squared minus y squared over r squared. That was a crazy r. Over r squared equals 1. So basically a hyperbola that has the same x and y radius, right? When you have one of those, so when you have a hyperbola that has a minus in the middle, you're going to end up with something like this, right? So when we have y equals the square root of x squared minus 9, we can understand that that must have come from a hyperbola. It must have come from a horizontal hyperbola. And in fact, one of the strategies I'm going to mention in the example that's coming up is if you have something like this that has a square root, sometimes it helps to sort of, like, and I'm going to box this off so we can look at it, square both sides. Like, look and see what this thing looks like. It would be y squared equals x squared minus 9. If I were then to sort of move the x squared over, I'd have y squared minus x squared equals negative 9. If I took one step further and divided by negative 9, I'd end up with x squared over 9 minus y squared over 9 equals 1. And my bet is that we could graph that. Like, we could sort of think about a graph that had a box that was sort of, 3 to the left, 3 to the right, 3 up, 3 down, and we could sort of even picture a horizontal type parabola fitting on the sides of this thing. And then when they ask you for the square root of that thing, we are looking at the function version of it. We're looking at the upper half if it's positive, or of course the lower half if it's negative. Okay? I'm not going to spend as much time going to this last hyperbola because it's very similar. Right? When you have a y squared minus x squared style hyperbola, in other words, a vertical style hyperbola, this is what the y equals form will look like. So when you see something like y equals the square root of x squared plus 16, we can understand that that must have come from a y squared over 16 minus x squared over 16 equals 1. Right? It must have come from a graph that sort of had that dotted box, and it had a vertical style hyperbola on it, and I would draw the bottom half, but because this is a function, it's just going to give me the top half. So the short of it is, lots of times when you see these y equals square root of x squared style graphs, they came from conics. So let's look at a few examples of that. So here's my first one. Sketch the graph of the function given below by showing it as a part of a conic section. So really the way that I'd recommend you do this is take this graph and sort of write it in its standard conic form. In other words, like square both sides and work through it. So pause the video and do that. So when we do that, we end up with y squared equals 25 minus x squared. Then if I move that x squared over, I get x squared plus y squared equals 25. We can tell that this is a circle. We can tell it's a circle of radius 5. Right? So when we go to our graph, we're sort of going with this mental picture of, hey, it's a circle with a radius of 5. It's going to look like this, right? But it has to be a function. I have to do a function, so it's either going to be the top half or it's going to be the bottom half. And in this case, because it's a negative square root, it'll be the bottom half of the graph. Therefore, we know that this function will be graphed like this. Right? So even though previously we would have no idea what this thing looks like, we can understand it by thinking about it as a conic section and drawing what we understand of it. So this is my last example. Sketch the graph of the function given below and then use it to determine its domain and range. So I'm making a connection here back to using a graph to determine domain and range. So I'd really like you guys to work through this one, work through the graph of the function by thinking about it as a conic section, and then once you've got the graph, come up with the domain and range. What I'd recommend you do is pause the video and put it in its conic form section, then look at the graph and sort of go through it step by step and check your work as you go along. So the first thing I'm going to do is I'm going to look at this as a conic. If I square both sides, I get y squared equals x squared plus 36. So then by solving, I can get y squared minus x squared equals 36. In other words, y squared over 36 minus x squared over 36 equals 1. Right, so what conic section is this? Well, because it's a subtraction in the middle, this is a hyperbola. And because the y came first, we know that this is actually a vertical style hyperbola. So it's going to be one of the ones that's sort of opening up and down. Right? So from there, you guys should be able to graph this. So if you haven't already done so, pause the video and sketch a graph of this thing. So I know my graph has this box that sort of goes, 6 to the left, 6 to the right, 6 up, and 6 down. So you've got sort of 6 this way and 6 this way. And from there, I'm drawing the I've got the top of the hyperbola, and I've got the bottom of the hyperbola. That's what that's what this would be. But this thing here is asking for only part of it. Is it going to be the top branch or the bottom branch of the hyperbola? Well, because this is positive, it's going to be the top branch of the hyperbola. And I should be drawing the asymptotes to make this a nicer graph. I'm going for a general sense here. Now that I have this graph, we should be able to talk about the domain and range. So I want you to sort of think about that graph, picture what it looks like, then try and come up with what are the domain and the range for this function. So the domain is supposed to be all of the x values. So if you look at this graph and you think about this function, how far does this function go side to side? Or think about it in terms of the function up here. What are you allowed to plug in here? Well, whatever you plug in is going to be positive. It's going to get 36. It's going to get even bigger positive. We'll be able to plug in anything. The domain of this will be all real numbers. Okay? What about the range? Right? What about the range of y values? As I look at this vertically, how high up and down does this function go? Well, these two sides of this sort of go in both. They go up and down, not up and in. They actually go up forever. Right? But down, we never go any lower than 6. So my range here will be the set of all y such that y is greater than or equal to 6. Now I'll note, we could have also figured that out by looking at this thing. When we plug things in here, it's only going to make that 36 bigger, which means sort of the smallest number you can get out of this is by plugging in 0 for x. Right? So I hope this makes sense, and I hope this has given you a way to think about how to graph this style of function, which is something that occasionally comes up on the calculus exams and less occasionally on the IB exams.